My apologies for being late. Welcome to truly the last of IEU's monthly lunch talks today. Yes, sorry, it's being recorded. So good afternoon again, everyone. Thank you for turning up to IEU's 13th lunch talk this year and the last one for 2018. As you know, the IEU holds these lunch talks every month on areas that are really useful to climate change, evaluation, development, and learning. And we encourage you to think of, people who are experts and global leaders in areas that are related to these overall sectors and themes that we might invite. Today, I'm really privileged to have Seth with us. Seth is a senior data engineer at AidData, and AidData is located at the College of William and Mary in the United States, and AidData is working very closely with the IEU to help us put together GIS data layers on GCF investment. So the idea really is that we create a GIS, or Geographic Information System, on each one of GCF's investments, so that we can analyze a lot of the other physiographic and socioeconomic data that are related to GCF investments and also correlated with other investments that are coming from other agencies, other multilateral efforts, other organizations that are working or are co-located in the same area. So geospatial disaggregated data can help us to do very different analyses from the time series data that we basically end up collecting, if at all, to do very regular analyses. Geospatial data also can be extremely useful in giving you a visual idea of what's happening. About 20 million years ago, when I first did my first GIS work, when I was looking at the World Bank, I was working at the World Bank and was contributed to set up the first GIS lab at the World Bank. We looked at whether protected areas can help to reduce deforestation or not. And so this was co-authored work that I ended up doing with my professor from Maryland. And we discovered that although protected areas are good at protecting, they don't necessarily contribute to reducing deforestation, primarily because they end up being located in areas that wouldn't be deforested anyway, because the threats in those areas are very, very small. So, these are sorts of analyses that you only get to do if you have geospatial data or disaggregated data. You also get to look at soil content, elevation, slopes, distance to cities, etc., and think about vulnerability in very different ways. So that's sort of part of the genesis of why we also wanted to work with AidData, and especially with Seth, and we're really tremendously lucky to have him here before the close of the year. So Seth has been working with the rest of the team at IEU to train us and make us somewhat more sensitive to how we can do these sorts of analyses. Seth has been instrumental in doing a lot of geospatial impact evaluations while located at AidData, and has also contributed in significant ways to understanding the GEF's overall impact, which helped to inform the latest replenishment that the GEF basically underwent. I'm going to give the mic soon over to Seth, but a couple of words in terms of how the afternoon will run. Seth will talk for about 25 to 30 minutes, and then we'll open it up for a Q&A, and we'll try and take two rounds of Q&A. Please try and keep your questions precise and fairly sharp so that we can get as much participation as possible. Clarificatory questions during Seth's talk are absolutely fine, but discussion questions for only later, please. And last but not least, our next talk, IEU talk, will be late January, and we'll announce it in early January. With that, Seth, over to you. Oh, yes, one more thing. This is being recorded, and the link will be available on the IEU website. Meanwhile, please feel free to tweet this lunch talk and any part thereof Research also tells you that if you tweet, you learn the stuff better. So that's all.
Thank you, Joe. Thank you everyone for coming here today. So I'm going to be talking to you about machine learning techniques for project evaluation. There's some non-machine learning stuff in there as well. So we're going to be looking at the question, how can we measure, how can we leverage geospatial data and machine learning methods for development? We're breaking this down to 3 different parts. Measurement, looking at how we can use machine learning techniques called convolutional neural networks to estimate outcomes of measures such as poverty indicators and other surveys. We're also going to be looking at transparency through data and distribution of that data. They include Geo Query data on development and administrative boundaries, and the platform distribute all that, as well as barriers to access to geospatial data. And finally, we're looking at 2 different things under the evaluation category, a hybrid econometric machine learning technique called Causal Trees, as well as a simulation-based method for incorporating uncertainty data into your analysis.
Excuse me, Seth.
I don't think your mic is working. Can you tap it? Oh, okay.
Just swap anyway.
And closer. Yeah. Be a rock star.
So first off, we're going to be looking at the convolutional neural network approach. A little bit of background about the measures we're looking to estimate using this technique. It would normally be procured using household surveys. This is usually the ideal method of collecting local household development data. Unfortunately, as you may know, these could be difficult to collect due to issues in the field such as conflict and non-permissive environments, as well as just the cost and time cost associated with getting the coverage needed in terms of space and time. This is most prominent in low-income countries where we want this data, and these data gaps compared to the developed world tend to just keep growing when you don't get these data to suggested intervals. And the biggest issue is once you're missing this data, there's no way you can go back in the field and say what was happening 5 years ago. So over the years, researchers have looked at ways of estimating these indicators rather than measuring in the field. One of the most prominent ways of doing this has been nighttime lights as an indicator of economic activity. There's been a number of papers showing how strong correlations are between nighttime lights and economic activity. We have nighttime lights data with local coverage and a pretty good historic record dating back to the 90s. There are 2 different platforms that offer this, one at 1 kilometer resolution, the other at 750 meters, which is pretty good. Biggest issue with nighttime lights is that the areas we're interested in, or rural areas, those are the places where it's hardest to pick up light with these satellite sensors. Also other issues, saturation bloom, just getting the true resolution you want to measure development. Most recently, new work out of Stanford started showing that you can use these machine learning methods to improve upon just using nighttime lights. They did their initial work on household consumption and assets indicator of poverty. And as you can see here on the right, where nighttime light tends to fail in the poorest areas, these machine learning methods were significantly better. The initial work was using very high sub-meter resolution imagery, but subsequent research in this area showed that even Landsat 7 imagery, which is 30-meter resolution and much more readily available, was still effective at estimating these outcomes. This work has also been expanded into areas beyond just poverty, showing that this does extend to other outcomes. Groups have looked at infrastructure and a few other health ones out there. So what are these convolutional neural networks and how do they work? Well, convolutional neural networks are just a type of neural network that are extremely effective at identifying features in images. These normally are used with images of houses, cats, dogs, traditional images you expect, but they also work very well with satellite imagery, picking out features such as houses, roads, and anything else you can identify. So what actually happens in this process is you have a set pattern that the computer wants to look for, such as a line or a shape, and it goes through a convolution over the image, or is striding over this image, looking for places where it identifies that pattern. As you go through these multiple layers in the network, the patterns get more and more complex. So early on, you're looking at very simple things that are shapes, lines, colors. But as you go deeper and deeper, you start seeing things that are more meaningful to your applications. Maybe it's a car or a house. This is just an example of two basic diagonal patterns going over an image, and as they do, each time they pass, they create what we call a feature map, identifying all the places in the image where it identifies that pattern. It does this dozens of times for each filter at each level as you go deeper and deeper through the network. When you pull this together, multiple levels of these convolutional layers as well as additional layers, you start off with your image, and as you can see, you start in the early layers getting something where the outline still looks humanly recognizable to a car. As you go deeper and deeper, you can no longer make out what it's actually showing you, but what it's representing is very important complex features. So it might be, this is what the side of a car looks like, this is the top view, this is a wheel. Ultimately, you have a layer M that would do a classification. So we're not looking at cars, we want to look at satellite data. As I mentioned, Landsat 7 is a great option for this compared to other satellite imagery for a number of reasons. We have global coverage, we have a spectral range across 8 bands that gives us a lot more information than just the standard red, green, and blue you'd see in an image from your camera. We have good historic and contemporary coverage of areas around the world. A 16-day revisit frequency, so every 16 days, every place on the Earth has an image taken of it. There's also predecessor and successor platforms, so if you want to do really deep time series analysis and you're worried about whether you're going to still have this platform in the future, there's additional satellites. As mentioned, there's 30-meter resolution, which is relatively coarse compared to some satellite imagery, which can be sub-meter, but work has shown this is still effective for these development applications. There are some caveats, such as a hardware failure aboard this. Suppose I'm using that and a later time which does have ways of.
So how many satellites is it?
That is one satellite, and that's it.
And it manages to cover every part of the Earth every 16 days?
Yes. Sometimes there's clouds and other issues with the atmosphere, but usually when we aggregate up to at least monthly, there's an update to get a good picture. So to actually implement this, we use a high-performance computing cluster, William Mary, with a bunch of fancy graphical processing units on it to run all these neural networks in a reasonable amount of time. We use a type of convolutional neural network called ResNets. If you're familiar with neural networks at all, you know that going very deep using a lot of layers can make it very difficult to run. ResNets essentially find a fancy way of allowing you to use deep networks without getting any of the drawbacks of computational costs. The next thing I want to mention is very important. It's something called transfer learning. So a big part of machine learning is having enough data to train your application efficiently. Development, we don't always have a lot of that. If we're using survey data to train, it's fairly limited. So what we do is, instead, we pre-train it on a different set of images. So in this case, it's something called ImageNet, which is 14 million images in 20,000 categories. These are completely different from satellite imagery. But very interestingly, work has shown that even using different images, the core things your neural network will learn at early levels are still transferable. Even though you're training on a dog, cat, house, it's going to learn things like lines, edges, shapes, colors. Then what we do is we use our application-specific data to fine-tune this pre-trained network, and it's very effective, way more effective than just using random weights in your neural network. So how do we get from that to an actual application? This is one case where we're predicting non-permissive environments at AidData. So we take in the satellite imagery and nighttime lights for our convolutional neural network. And the short version of what we do is instead of feeding nighttime lights on their own into a model, which could be a regression model, another neural network, or anything, we pull feature vectors that the convolutional neural network use to classify different levels of nighttime lights or anything else you're interested in, and plug that into our standard model. This is where the real benefit works. What the convolutional neural networks are picking up in those features is much more closely associated with their outcome than nighttime lights alone. These then go to produce a surface, a map of their outcome, and in this case we fed some other things, Afrobarometer survey data, and content information into our model as well. Any questions on that part? Sure.
So what's a CNN? I mean, what is the neural network? What does it look like?
It's, in practice, it's a bunch of code from different Python packages that are implemented, and they run on a graphic processing unit.
Okay. So there's no visual associated with it. I wouldn't look at something and say, oh, this is a convolutional neural network.
No, I mean, representing it is that you can do different ways of sort of pulling out what's happening at different steps of the network, but essentially it's
Yeah.
So the next part I'm going to talk about is data and distribution and transparency. This is going to be for producing spatial data on aid administrative boundaries and leveraging high-performance computation to improve how we distribute spatial data and make it more accessible for everyone. So first, tracking underreported financial flows. This is the methodology for collecting data from opaque donors, such as Chinese aid, where they don't publish any information on their projects. That AidData created in 2013.
That is not speaking on behalf of GCF.
So what this did was essentially we had a room full of students locked in a basement somewhere, and we had them go through thousands and thousands of media sources and other articles that were potentially related to Chinese aid. What they did was classify every single article as this contains some information on Chinese aid or it doesn't. What we did was then we fed that into a machine learning application called a support vector machine to train it to recognize what was important in these articles and associated with aid projects or not. This machine learning application then went on to do millions and millions of these articles and classifying them. This is the first stage of a broader process. So after it broke down those millions ran for a couple months, it broke it down to tens of thousands. We gave it back to the students, locked them in their room again, and they actually coded those for the product information that was in them. This saves us a massive, massive amount of time, made it possible to actually go through this entire collection of what's going on with Chinese aid, and now this is the most comprehensive, definitive set of information on where Chinese aid products are going. After that process of getting the product information, we then geocoded it. So what is geocoding?
How long did it take you to do that part?
Running it?
To just get the database together of underreported Chinese aid flows?
That was probably about 2 years, and there were periods in there where it was more activity than less. But before the machine learning part, we had a smaller subset of that data that was done completely manually. And that was, there were probably a couple of years in between there when it was published, but that also took a couple of years. So geocoding is a process of looking at this product information that doesn't have spatial data associated with it, but maybe has place names in there or some description of what was going on, and actually assigning it coordinates or drawing a polygon around where the building or town is. This is really good because you can go back and do this historically for projects that, as I said, didn't have this information. You don't need to do it while the project is going on. So where do we get our information from? Usually it's project documents. It could also come from local governments or donor systems, or the tough methodology, third-party sources, like I just mentioned. What we do is we geoparse, that's where we find all the information there, and then geocode, that's translating these place names into actual locations on the ground coordinates. Key aspect of this is precision. Sometimes we can't find good information about the project. Sometimes we can find the exact description, but there's no reference or map about where it actually is. So what we always try and do is draw a shape around the area that's the smallest shape we can get. So it might only be the district that we can draw for a well. Sometimes we can draw maybe the block it's on, or sometimes we get the exact coordinate of where that well is. Machine learning efforts have gone into this for years now, and they continue to fail compared to human geocoders. They just struggle sometimes when we make them too lenient. It ends up coming up with millions of place names that are just random words that clearly aren't locations. Make it too strict, it fails to recognize spelling that's slightly different or contextual factors. Something interesting that's been going on the past year or so is we've had students working on taking this machine learning and sort of retrofitting it. So instead of trying to get the locations themselves, it's just sort of highlighting it. So it assists the geocoders. It says, maybe look in this part of the document. We think there's something relevant there. Next is Geo Boundaries. So this is just a fully open source collection of administrative boundaries that we provide all these sorts of information about where we got the data, what government or organization produced it, when it was from, that you can take and do whatever you want with. We built this because all of the data on administrative boundaries out there either have restrictions on what you can do with it, they don't tell you where it's from. This is about the past year or so we've gone to doing this. It's 600 sets of boundaries for 196 countries. We have students sometimes going out in the field, talking to all sorts of governments, trying to get this information and continually update it. So now that we have this geocode information, we have geo boundaries, we have all sorts of other satellite measurement data out there. What do we do with it? How do we get this out to people? For this, we produced a platform called Geo Query. So what this is essentially doing is just integrating all this data. We have boundaries from Geo Boundaries as well as another source called GATM that we treat as a unit of analysis where you want your information for. Then we have 50 plus covariate outcome data sets for aid, economic development, infrastructure, population, environment. Tons of stuff, and we're constantly adding new ones. What this platform does is it takes the boundary, you select the boundary you want, you select the data you want, click OK, goes off into a high-performance computer. It does something called zonal statistics. This is essentially just taking the boundary data or vector data, taking sort of satellite surface or raster data, and it's putting those two together. And it's aggregating them with some statistical function like mean. So this is just a quick example of a boundary state, precipitation, and how you can aggregate that to get a value for your boundary. GeoQuery just does that really fast without having to have any knowledge about spatial data or having any of the software in your computer to do this because it can take a long time to run. Once it's done, it just emails you a link where you'll have a permanent page, all your data, documentation, information about the source all the data came from. That link will stay there forever, and your final result is just a CSV. You don't have to know how to use spatial data. You can load this in Excel, data, R, whatever you want to use. You can still get the benefits of having spatial information in your analysis without having to spend all the time of learning how to use GIS software or anything else. Any questions on that? Yes.
I have actually one comment on the.
Can you, Pierre, can you use the mic? So, given that we're recording. Not that I was following that rule.
No, I just have an observation on the reliability of the final output. Given that the whole system is fed by information from the donors information system, I'm just asking myself whether the final output can be reliable if the initial information itself is maybe not reliable. The other thing is about privacy of the whole thing. You may have seen today that Google CEO was actually testifying in front of the American Congress about data privacy. I'm not sure on regulatory and policy aspects whether it actually is legal to just say that such community somewhere has received aid without the consent of those communities, and what has to do with privacy.
I can't say I personally had talks about that with our donors. It hasn't come up. But we have had talks when we've been geocoding data with groups where we can't include certain aspects of the financial information in the data. We could look into that and get back to. I don't have any examples off the top of my head, but as for the first part, it is limited by the documentation. The geocoding is only as good as the information we get from the donor, but we do try to generate sort of quality metrics about the amount of information we have in the system and how that was used to geocode to reflect whether we think it's valuable or not. Usually before we do any geocoding, we try to do sort of like an assessment to make sure the information there's sufficient information to geocode this to the quality we're happy with. So for the next section,
Seth, sorry, one other clarificatory question. Is there any way to show confidence or uncertainty in data, especially?
yes. So there's some fields in the actual geocoded output that describe the level that the project was geocoded to, it was able to be geocoded to, and what we think the ideal was. So if we have a well, we know that it should be a well at the end of the day. It should be a very small point location. If the best we could do is a state, we would have sort of conflict between what the final geocoded field was and the intended field was, which is used to basically flag that item in the result. And the last section of this presentation, I'll go into explaining how we can deal with some of that uncertainty in geocoded data.
I have a question.
Yes.
Well, I believe that reliability of data is important. At the same time, precision in the interpretation of the data is another. It looks to me like an X-ray picture of a human body. And it's extremely important to how to read this X-ray output. In the same way, do you have any research into this art or skills in interpreting the data
Yes.
in education system?
So this is one of the biggest things we try to tackle when working with researchers who use this data is making sure they are being intelligent about interpreting what we give them. A lot of times what researchers want to do is they just want to take all the data and just use it as is. Sometimes what we've seen is when we have multiple levels of precision, they'll just drop all the ones that are not precise and ignore all that data. So as I mentioned, the last section is going to go specifically into dealing with some of the methods to overcome these issues. Before I get to that, though, I want to go into one more aspect of machine learning called causal trees. So this is sort of a hybrid econometric machine learning approach to evaluating projects. I'll just say as a sort of pre-thought, this tends to be very effective at a portfolio scale when you have more data. And that's the common theme with machine learning. The more data you have to feed into it, the better it's going to work. So a little bit of background. Doing an evaluation, trying to get a causal inference aspect out of the evaluation is known as sort of a potential outcome framework. If you treat one area, you don't treat another, what's the benefit of doing that treatment? So the common way of doing this is randomized control trials. Essentially, you subset one part of the group, randomly assign a treatment, don't do a treatment in the other group, that's your control. This is common. You might have recognized this from medical trials or something on websites where they change a part of the website and see how it affects users. Key thing to keep in mind with development projects is that it's not always practical to do this. Sometimes it's not moral. You have enough money for 10 health clinics, you don't want to build 5 of them, just leave the other 5 areas as controls just because. You want to get as many, you want to do as much good as you can. It's really expensive, difficult to both monitor this over time and just implement this in the first place. There's also not much machine learning in this space, but there is machine learning opportunities in quasi-experimental research and science, which have essentially the same concepts, just implemented in very different ways. So the goal here is to use existing data that didn't have any of these random distributions to it, and still establish some form of causality, learn something from these historic project portfolios. You can do this post hoc, but you lack that intentional random design, which historically has resulted in issues with the sort of statistical robustness of your evaluations when you use these methods, but there's now ways of incorporating new methods to deal with that. There's some details about how you use the different dimensions of data, which you incorporate into this analysis, that robustness. So something called Neyman-Rubin causality, that's kind of the space where a group, 2 researchers, Athy and Invens, are leading the machine learning work in this space right now with causal trees and causal forests. What it essentially says is if you have a village, you could have 2 potential outcomes, one where it's treated, one where it's not, theoretical space. And then the difference between that is how effective your treatment or a clinic was there. When you have all these treatment control units, they were assigned, regardless of whether it's assigned randomly or not, you essentially want to match them based on various dimensions of socioeconomic, demographics, environmental conditions, that you have your treating control or as similar as possible. So you don't have to worry about anything other than your treatment playing into the outcome. At the end of the day, all of this is just trying to represent what a randomized control trial would be. So where machine learning fits into this space is first that you can't observe the treatment and control for a single unit. That's why you're trying to find two that are as similar as possible. But if we don't have a randomized control trial, ideally we would just look at the exact same one. But something really interesting now we can do is we can use neural networks. Even if we have a treated unit, we can simulate what it would have been like if it wasn't treated based off of the pre-trends. This is very, very new. I don't have a lot of information on this. We're talking about the second part, where if we have the assumption that the causality is identical across all units, it's not valid, we can use something called causal trees. This is assuming that there's different subgroups of this broader treatment control units where effects might be possible that you wouldn't see across the entire population. So there might have been only the northeast corner of the country is effective, or it's only places where people have incomes over 50,000 where treatment was effective. And these causal trees are going to allow you to isolate that. So these are very similar to a normal classification tree if you're familiar with those. This basically just breaks down data. The key thing here is that the way it breaks down isn't just across the entire population, but it does it so that it matches units based on whether they're treatment or control. You can identify an average treatment effect for each of these final nodes, which are just a group of treatment control units in there. And so there's not really any ideal version of this tree. There's lots of different parameters you can set based off of these splits and definitions of what's important to you to have in your treatment control group. You could say there's certain characteristics that must be there. It must contain populations that are both male and female. It should have at least 5 tree control that can define how deep your tree goes.
Sorry, could you? So in this diagram, F1 is one type of causal relationship between A and B and A and C.
Yeah, so when you go to examples, I'll make this a bit easier.
Okay.
This is, you start off where the first split is based off of the amount of disbursement for the project.
You'll have to back up and explain what the diagram is set. I don't think we sort of got it on the next one. So either on this one or on the next one.
So A would be your full population of projects.
Okay.
All the treated and control. B would then be a split that says this is everyone who is living in the western half of the country. C would be everyone living in the eastern. This would then be everywhere in the western half of the country that has at least 3 inches of rainfall. This would be everyone that has less than 3 inches of rainfall.
So is it just a form of stratifying the population then?
Essentially, based off of spatial characteristics, characteristics, with the caveat that you have conditions. Every time you do these splits, you say you have to have a certain number of treatment control in there.
Can I ask one question? What is then the distinction between the classical heterogeneity analysis, like Joe indicated? This is, I would say, the normal impact evaluation or any regression strategies. You could do different sampling, break the data into different categories, do regression or estimation within that cluster.
So
what does differentiate this?
The key thing there is that normally in ideal scenario, you would want to pre-specify in your research design what you are breaking those groups up into. You don't want to sort of do
data mining
to find what works. This has no human involvement. The computer is designing those branches and splits. So that adds a bit of robustness and validity when you're trying to get your research out there. So expanding on these causal trees, knowing that sometimes they might not be perfect. You could have one case where the tree the machine learning aspect of it just does something a little weird that doesn't really make sense. And sometimes that just happens. So what we do is we do something called causal bars. And that's essentially breaking your data down and running thousands of these causal trees instead of just one of them. for different subsets of population, split in different ways, different factors that the computer decides all on its own. For each of them, it runs a tree, and it essentially averages them to get your overall effect. So in this little image on the right, you can see where the truth is a relatively tight. The causal tree, it's very large potential errors. Causal forest, it's much closer to it by averaging those effects. This is really important to use when you have a small sample size in particular. It allows you to still get some of the validity out of your data set. So there's one example of where we've used this is with a global environment facility looking at land aggregation and vegetative density. This is a very small version of the tree. It's splitting, so first on precipitation, disbursement, longitude, urban distance, longitude and precipitation again. And on the right here is the important part.
Global data.
Yes, this is global data. So what was really important, this is the aspect of the causal forest. This is the uncertainty over all of those thousands and thousands of runs of those causal trees. This is a better example of what your tree might actually look like, and I'll tell you this from experience, this is still a pretty small one. But it's very cool because when you look at what these are telling you, when you go through them and look at the final nodes, track it down its path, there's still some really meaningful insights in there. And we saw this with the jet. These different dimensions ended up having a real impact on where they're putting their money in the next cycle. So key things we found was that this 5-year threshold was consistent across all the different projects. Before they had a 4-year cycle, and we found that really you need at least 5 years to start to see these impacts over space and time. Now in their next cycle, they've switched to 5 years. So this method is still being developed. There's some issues with it, but it's already showing meaningful impacts. It's going to be more effective, cost-effective, and practical than randomized control trials in many cases, and it's going to do more than traditional program evaluations that don't incorporate the traditional elements of spatial data could do in some cases. Last thing I'm going to talk to you about is something called geosimics. This is going to deal with how we incorporate that uncertainty in geocoded data. This example, we're going to look at Chinese infrastructure aid in the greater Mekong Basin and its effect on forest loss. These were projects between 2005 and 2010. We did a fairly straightforward regression model of these, looking at controlling for air temperature, precipitation, nighttime lights, and a few other aspects associated with how the projects were implemented. So when we're geocoding, going off from before, sometimes you have very specific codes, you know exactly where these projects were. Sometimes your best you can do is a district. Worst case scenario, all you know is it's somewhere in a country. For unit of analysis was the sub-district. So when you're dealing with these issues of imprecision, the traditional way people have incorporated this analysis, they drop the really imprecise data, maybe the country level, state or course there, or they make assumptions for those course locations and say the aid was probably distributed based off of the population across the country, and then they just model it that way. Neither of these are great. So we thought, what happens if we simulate these true locations across the country? Here on the right, you can see dots moving around. So in these cases where there were points across the country, we essentially run this thousands of times, dropping the point at different places in the country, seeing what happens. So the second plot is the number of projects in each district. So each time you do a different run of this, the number of places change because they're all random, and you can see it's all over the place. Similarly, when you actually look at the effects over those simulations, it's pretty varied. So that's not great. But what if we find a way of modeling that to incorporate that information and find the true or close to the true impact? So based off the information we have, we start off with what's called the naive model of where data is. And what we do is really interesting. We intentionally add imprecision. So if we had something at the district level, we really want the sub-district, We'll coarse in that and simulate it at the state level, and the region level, and then the country level. We're moving down the wrong direction, but giving us those trends. And what you can do is you can work backwards and estimate what the true value should be close to. So just to give you a real example of this. Here's we start off with a naive model. We drop all these points from different simulations. This is just
Sorry, what are you modeling?
so this is the example from the effect of aid on deforestation in the Greater Mekong Basin while we're increasing the spatial sensitivity.
I have a very stupid question. So, is this the coefficient on deforestation?
Yes, this is the coefficient AIDS effect on deforestation, and this is the level of uncertainty.
Okay.
Lambda. So you can see here, this is the result of looking at these trends in thousands of different cases. And what we get is we have the average of that is our new estimate, but we also, most importantly, have these errors associated with it. And here's the really cool part. These are the two cases where we looked at it with just dropping the spatially imprecise data or assuming information about distribution of aid based on population. What we see is that there's a positive relationship between the effect of aid and deforestation. And that's a big deal to say that, Chinese aid is causing deforestation. But when we incorporate this uncertainty there, look at our standard errors now. The estimate is still positive, but now we really can't be sure about it anymore. It's crossing over zero. So going back and looking at past research that used these other methods, considering whether they still hold up when you account for this uncertainty is a big thing now. That's it. Thanks.
Thank you. Thank you, Seth. Questions, folks? John?
Thank you for your presentation. It was very informative and very difficult, but it was very exciting learning. So I would like to ask from the practical perspective. For example, GCF has got hundreds of projects that were submitted, and up to now 93 projects were approved. Do you think that maybe 300 number of projects that were in the database can be a basis we can build up the machine learning, causal trees, and so forth in terms of various criteria to see which kind of projects were approved and what were not approved? So do you think it's practically can GCF start thinking about applying machine learning in evaluating and assessing the funding proposals?
Should we take a round of a few questions?
Sure.
Yeah.
So, MG, thank you so much, Seth, for the presentation. That is very interesting to me, especially because I'm dealing with the portfolio data in this set and studied in GIS and wrote my master thesis by using the ArcGIS with the regression model, geographically weighted. So, and I would like to bring up a question that I had when I wrote the thesis. It is very relevant to this presentation. So to me, the statistical outcomes that you show by using machine learning here is just showing the physical phenomena, but it's just one-way information. But given the title of our today's talk, that is machine learning technique for the project evaluation. So I was more interested in the linkage, the relationship between the statistical outcome in GIS or machine learning and the specific indicator that we would like to evaluate. For example, let's say economic indicators, economic activities. we want to evaluate economic activities. And you said the night lights is the measurement of economic activities, but I couldn't see any of the linkages through the machine learning technique here. So I wonder if you have any good idea how we can use the machine learning to evaluate projects, because I don't think the the statistical outcomes give tell us the heterogeneous effects due to the economic activities. So, for example, the night lights measurement doesn't tell us the economic activities indicators. But you said there are so many documents that are showing the linkage between two, but through the machine learning, how we can evaluate such a things.
Thanks, Jay. One more question, a couple more. Go for it.
Yeah, I'll just
Sunny,
try to
and
raise my voice without a mic. So thanks for the presentation.
No, we need to, because everyone's a rock star here, everyone's getting recorded.
Okay. I guess I'll try to join the fairness room. Thank you. My question is kind of the unique characteristic of GCF projects tend to be, instead of being specified into a certain region or a country, a lot of them actually tend to be done in global scale. And unlike a sector-specific projects, a lot of us, or some of our projects tend to be very focused on the financial element of it, and we kind of leave it up to the implementing entities to do various things with the financial inputs that GCF will be providing. From your explanation with my limited understanding in GIS and machine learning, I'm pretty sure there's a way to address this kind of more dispersed layers of information and inputs, and I'm afraid that it might be too premature to actually get the very clear answer to this question, but are you also planning on actually coming up with some kind of data set or framework that could assist us in evaluating the actual efficiency of the projects or resources that we're putting into projects that covers global scale without any much of a symmetrical information and geocoding aspect on different sectors?
Thanks, Sunny. Saul?
Thanks so much for this brilliant presentation. I think you showed us what one can do with machine learning and geospatial code data. And if you could also talk a little bit what geospatial cannot do. One thing I could imagine is in all the estimate you showed, we know the magnitude of the effect, but GIS analysis could not tell us about the how the mechanisms through which that would be delivered, and then if you don't observe any impact, and then why. And that brings to the idea of then combining data sets, in a way using socioeconomic surveys combining with geospatial data to kind of supplement that, if you could comment on that. The second point briefly is in your simulation you did, that's some sort of waiting for uncertainty in a way. Can I explain it that way? The last one you said, you did a lot of micro simulation, you kind of get much more lower estimate. In a way, if that data point is very imprecise, then you kind of did a lot of simulation, then kind of weighted that. Is that another way of expressing, or am I getting wrong?
Yes. Yeah. That's essentially what you get.
Okay. So thanks all. So 4 questions. Sure. Starting with John, then G, Sunny, and Sol, and then we can do another round probably.
So the types of projects accepted. I think even without the spatial data aspect of that, there's still opportunities just looking at the proposals for those to understand the context, the ones that are accepted and not, and comparing those. I think there's lots of opportunities there across different machine learning applications. I don't have any specific things, but just off the top of my head, it seems like there's definitely potential there for having, as long as you have enough information in the documents about the different criteria associated with each of them, which I believe you do, it could work.
Just one extended question.
Yeah, go for it. And also, John, I hate to speak for you, Seth, but if you wanted to have a bilateral conversation with Seth, just come up to the 17th floor sometime tomorrow morning.
Right.
And just feel free to chat.
Great, thank you. Yeah, I want to extend the question to my question was that actually our project documents, proposals, are in paper format, not necessarily in digitalized, or some data are digitalized, but I mean that according to your explanation, you are talking about textual analysis you can do on all those project proposals you received and find out some patterns in causal trees to see if the proposals expectations can be accepted by the GCF and so forth. So is it correct understanding?
Yes, I think even in cases where it's not already machine readable documents, there's something called character recognition.
Exactly, we can do that work beforehand.
Yeah. So yeah, if there's database work for that. Second one was about the statistics of the machine learning stuff. I didn't go too deep into that, but so the original paper published out of Stanford, that this was in Science, was a pretty big piece in 2016. It goes much deeper into proving the actual statistical component of this and looking at the statistical effects of nighttime lights, showing how the new outcome services for poverty indicators improved upon that and were still reliable when used in tests across, I can't remember, it was 5 different countries in Africa, and they had an extremely robust framework for testing the effect of those data sets on household assets and consumption. I could send you that paper. It's got a lot of information there. I think it would be great for what you're talking about.
Yeah, thanks. So, can I?
Yeah, Jacob.
So, in that document, the machine learning techniques was used to analyze the linkage.
So like when I say like be a rock stars hold their mic really close to their hands.
Sure. So in the document you just mentioned, the analysis is done by the machine learning techniques or regression models. Or
this wasn't an analysis; it was just evaluating the correlation, the ability of the new outcome when used in a fairly simple model to predict the survey indicator data. So it wasn't a full analysis, but it was sufficient to prove the robustness of the new measure. The next one was about valuation, I think. So I think this depends on a lot on the measure of valuation for each project, which can be pretty varied. We did some work with the Jeff where we're actually trying to develop a valuation for all their projects in terms of biodiversity and carbon storage. So those are 2 potential outcome measures to go against, and our valuations is a little tricky because at the end of the day, your actual dollar value effectiveness of these projects, it's based off of saying a certain amount of carbon sequestration is worth X dollars, and looking at the literature and experts out there, that range is completely massive. And biodiversity is kind of similar. It's really hard to put a dollar value on trees and animals and stuff like that. But there is a basis in using these causal trees for doing work like that. The last question was about what GIS can do and cannot do. So at the end of the day, it's all about just whether you have data on what you want to measure. That's not the fancy answer. Using that in analysis, the biggest thing to consider, especially with these machine learning-based methods, is that a fundamental statistical assumption of them is that you have data on everything that could matter. So if you have some unmeasured confounder that you don't have data on, you essentially lose all statistical power of this application. So that's a big thing.
Seth, sorry,
everyone, I also want to acknowledge Max, who's the president at IEU, and who's privileged us with his presence today. So thanks, Max. Great to see you again. And I wanted to follow up on Max's question, which is, do you provide any support on how to interpret geospatial data? And do you remember the question you asked about looking at the human body and the X-ray and knowing how to interpret it? And
It's a bit of a tough one to answer. It's always going to be very contextual. Usually, this is the kind of area where I and other folks at AidData tend to have the expertise in working with spatial data, but not necessarily the sectoral expertise on what the data is actually about to interpret that in context of analysis. That's where we always try and work with partners on something. So when we're dealing with evaluation of biodiversity and carbon storage, we didn't come up with our own evaluation metrics. We went out and looked in the literature and talked with other folks at other universities about what the best way to evaluate that and measure it is.
Well, actually, the reason why I was asking that question was because you're affiliated with William and Mary. That's primarily a research and education institution, and perhaps what you do can be sort of portrayed to the education part of the university, and there you can have some synergistic effect.
Yes.
So I was wondering whether that attempt has been underway.
Yes, so my boss, Dan Rumfola, who's also part of this work, is just started a data science program at William & Mary this past year. And spatial data and understanding how to work with data, the caveats, best practices is a big focus of that program.
but maybe IMU can start a program, and we'd love to see how we can collaborate. Okay. Any other questions?
I would like to ask one.
Yes, please.
Hi, this is Nevi from ICT unit. So my question is mostly about this neural network that you mentioned, the CNN. So, considering it's an artificial intelligence, process learning, self-learning, so how much data do we need to fit first that this framework lets neural networks start to learn self-learning experience? Because, I assume we need a lot of data once it starts to learning process. So is there any percentage, any expectation there?
Yeah, there's no hard number to say you need 1,000 images, but you generally need a lot. So that's where the transfer learning aspect I mentioned comes in, because this would not be possible without that. There's just not enough of this.
Is there a minimum, or let's...
I've heard numbers, so in the machine learning space, it's always sort of best practices and guidelines. No one ever says this is the number. I've heard hundreds of thousands as sort of the minimum amount of data you have. That ImageNet data set is 14 million, and that's sort of the standard for convolutional neural networks. When we were doing our most recent example with across Tanzania, looking at poverty estimates, our sample size after the transfer learning part was, I think our training and validation set combined was about 4,000 points. So that's 4,000 to fine tune. You have to use the 14 million to do the basics.
Okay.
And interpreting whether that was enough to do the fine tuning is a whole other thing. I like to think it was effective. That's still part of the literature, just ongoing, trying to figure out those minimums, trying to figure out what works, different types of data.
Okay, thank you.
Saul, did your question get answered?
Partly. You did not answer the question about the why, the how.
Can you repeat that part?
I do that part. No, the question is using only GIS data.
Limitations.
The spatial data. You cannot answer the question, why did you observe the impact? If there is or if there is not. And the second part is, what are the mechanisms through which you observe that impact? That's where the importance of doing socioeconomics and qualitative data work, combining with geospatial data, to have a package of that. Just want to comment.
Okay, so it's a comment.
Okay.
Great. I'm sorry,
Okay, thank you everyone for coming. So a quick announcement. I had it on Google Authority that our next IEU Lunch Talk will be on the 19th of January on meta-analysis. And we have colleagues coming from Exeter, University of Exeter, who will be coming in talking about meta-synthesis and meta-analysis methods, and then also show examples of that. So that'll be on the 19th of January, and we'll of course send out a note to all of you. Thank you, Seth, for your talk. It actually combined really well because last week or the week before that, we had a talk by Juha Vito, who's the head of the Independent Evaluation Office of the Global Environment Facility. And one of the things that he pointed out was that some of this work had helped them to show that JEF investments were only making an impact, if you remember, after 5 years of closing of projects. Yeah, and that was an important message that they took to council. And so we didn't put the two of these talks together. They just happened serendipitously. But it was nice to sort of see that one of the things that Seth also talked about was how, from the AidData side, and they were responsible for doing a large part of that analysis, they used some of these techniques in machine learning to show some of that work, right? So thank you, Seth, for that. And we, of course, are looking forward to continuing our collaboration with you, which will continue into next year. Seth will be here till Friday. John and others, if you want to come by and chat with Seth tomorrow morning, the first half is, I think, free. Please feel welcome to. And then next year, another colleague from AidData will come and spend about 3.5 weeks with us up at IEU, just so that we can get the rest of the team, get some experience with hands-on work. So that's sort of our plan. And with that, thank you very much, everyone, and have a great New Year.